Okay, so welcome student, welcome to today's lecture. Mm, this is MA415 Algebra. Okay, and then this is lecture number 20. Okay, now recall that we are discussing about two concept last day. So one concept was this zero divisor. Okay, and another concept were units, right? Units. Okay, so zero divisor are those which are non-zero element of the ring, such that you have another non-zero element, so that the product becomes zero. Okay, and for units are those non-zero element of the ring which has another element, such that the product equal to unity. Unity means one. Okay, so now I also ask you to check whether some ring property has zero divisor or not. That was homework, right? Now I would like to and discuss one more thing. You see that um, this concept, this collection of these say units. Say for example, R is a ring, so be a ring. Then we define this R. This cross is the um, group of units. Why it is group, I will tell you. Just group of units in R, right? Okay, so why this unit? See that under multiplication, this R star multiplication forms a group, actually forms a group. Okay, and this is obvious because you already know that R is a ring, so till now semi-group property is there, right? But for unit, you remember we assume that R has identity is not equal to 0, right? So this identity is always element of R dash, right? As 1 into 1 equal to 1, right? And for inverse, you choose if A belongs to R star, then by definition there exists some A dash belongs to R star R cross, such that A dash equal to A dash A equal to unity, right? Hence this A dash is the inverse of A. Right. So this set of all units forms a group and is called that group of units in R, right? Now you see that this group of units actually has a disjoint intersection with the set of geodivisors. Okay. So what I'm saying, so this is kind of remark, you just check it. I can also give you proof. Okay, so that this zero divisors and units, this they are disjoint. So by disjoint, what I mean that so inside the set of geodivisors there cannot be any unit. Inside the set of units there cannot be any geodivisors. Okay, so how do you prove this kind of thing? So the proof is simple. So you start, say let, suppose you have a geodivisor, so let A belong A be a zero divisor, and obviously by definition A not equal to 0, right? Zero divisor then by definition what happened, then there exists another non-zero element B belongs to B. Okay, let me write down B belongs to that ring R such that what happened is that AB is equal to 0. Yeah, it can be B also, doesn't matter, the proof is similar. Okay, so this, okay, now if so I'm claiming that A cannot be a unit because A is a zero divisor, it cannot be a unit. Now if A is a unit, then what happened? Then you know that then there exists some A dash belongs to this R such that obviously this is also non-zero element such that this A dash equal to 1, right? Clear? Now you see that A dash equal to 1, and then obviously A B equal to okay, so maybe I will write down other way. So A dash equal to 1 equal to A dash A. Okay, they are same actually. Okay, so because A is a zero divisor, so if you multiply by this by both sides by B, then you will have B equal to A dash A into B, right? And you know that B not equal to 0, that is also the definition of zero divisor. Okay, but the associative property of rings tells you that this is nothing but AB. Okay, so I am not writing dot every time because I am assuming that this is understandable. Okay, but AB is what? So AB equal to 0, so that will gives you A dash 0, and which is not equal to 0. Yeah, which is equal to 0. That is property of ring. I proved that, right? So you have something which is not equal to 0, but you just proved that that is a 0. So which is a contradiction, right? Which is a contradiction. Okay, so what does that mean? That means that A cannot be an unit, cannot be a unit. Similarly, the vice versa also, conversely also, if A is a unit, it cannot be a zero divisor. Okay, and also the converse part is true. I mean, you can easily prove. Okay, so maybe homework. You start with that A is invertible, so there exists A dash such that A dash equal to 1. Now, if A is a zero divisor, you write down, you find out that this. Let me write down. Okay, so otherwise, maybe conversely. Okay. If so let this A belongs to R, that R cross, that means A is a unit, so there exists A dash belongs to R or whatever R cross, such that okay, so A dash A equal to A dash equal to identity, right? Now if A is a zero divisor, then there exists a non-zero B in R such that AB or BA, whatever you can, I can see this is with a lot of generality, you can choose AB or BA, doesn't matter. because the proof will be similar. Okay, equal to 0. But what does that mean? Then you know that a dash, you multiply both sides, then it will be a dash into a dash into 0, so which is nothing but 0. But on the other hand, the left hand side is using the associative property, you will have 0. But it has equal to identity, so you will have identity times b equal to 0 and b equal to 0. So which is a contradiction because b not equal to 0, right? Again a contradiction, right? Contradiction. So units algebras are separate, they cannot be, right? Yeah, so now there are lots of examples. We could learn few of those examples, but before that let me define a nice object. So definition. Okay, so a commutative ring with unity 1 which is not equal to 0. So what does that mean? So I am not taking the trivial ring, unity having no zero divisor is called an integral domain. Okay, this is very important idea. Integral domain. Okay, what does that mean? That means whenever you choose an element here, you cannot have a divisor here. So what does that mean? That means given any elements here, either it will be unity or it will be some non-zero element which is not a zero divisor. So it contains non-zero divisor and unity. Obviously unity is there, okay, by definition. Okay, so mathematically what you can say? So mathematically you can say, so maybe actually let me write down. So that is if R, say, okay, if A and B belongs to R such that, I mean R is an integral domain, I'm assuming, then what happens? Such that A, B equal to 0, then either A equal to 0 or B equal to 0. Okay, so with the product of two non-zero element, so okay, so sorry, product of two elements is 0. I don't know non-zero or not. Then one of them must be 0. At least one of them. Both can be 0 also, obviously. So this is the property by which we need to check something integral domain or not. Okay, and I will give lots of examples. So maybe let me start with giving some examples. Okay, so the first and most easy example, whatever we have learned, is that ring of integers, right? Set plus dot. And now you see that this is an integral domain. Why this is an integral domain? Obviously this is a commutative ring with identity. Okay, so this is all the property satisfied. Commutative ring, commutative unital ring. Unital means unit exists inside the ring. Okay, and here you know that even if obviously the property tells you that if two integers product is 0, then 1 must be 0, right, to non-zero integer. So this is obvious. So is an integral domain. Integral domain. Okay, so this is one very important example, right? Now, let me give another example. So you see that residue modulo n. So let me take, say, this z mod, say 7z. Okay, and with that residue modulo operations. Okay, and now here also you see that there is no zero divisors. So obviously this is a ring, already we showed it, right? And see, 1 bar is the unity inside the R. Okay, and instead of 1 bar you have 0 bar, which is 0 element, right? So this is the 0 element, means additive identity, 0 element. And look at the other elements. So other than these two elements, there are 5 more elements, right? So 2 bar, 3 bar, 4 bar, 5 bar, and 6 bar. Now look at this, all they all are units in this R. Okay, so there is no zero divisor actually. Okay, now there is no speciality about this 7. Actually it is true for any prime. So if we choose any prime, then take z mod pz with that addition and multiplication. So is an integral domain. Okay, so what you learn? You learn that obviously there are lots of such examples exist, but the question is that whether integral domains are, what can you say about integral domain? They are field or not? For example, you say this is an integral domain, but this is not a field, right? This is not a field. This is not a field, right? Why it is not a field? Because there are plenty of elements which are non-zero but having no inverse. For example, 2 has no inverse inside z, right? Yeah, so let me give some more example, and then I will come characterize the finite integral domain, how they look like. Okay, so let me give another example. Say maybe let me define this q root d. And what is my d? So I will tell you. So this is of the form a plus b root d, such that a, b are element of rational number, and d is something not square. It's not a square element. So that root d is not a rational number. Okay. Now here you define this addition multiplication. You know the usual way, that a plus b root d and plus c plus b root d by usual way, a plus c plus this is d plus d. Okay, oh, there's too many d's. Okay, so let me use some different symbols. Let me use some different symbol. A plus b, and then a dash plus b dash root d. Okay, now it's fine. So this is a plus a dash plus b plus b dash root d. Okay, so this is the addition, and the multiplication is also similar. So if we multiply a plus b root d and a dash plus b dash root d, then what happens? Then these two will multiply, so a dash plus these two multiply b dash b dash into this sorry b dash into this d. This will be the first element, and then your coefficient of root d, what will be that? This into this, so this will gives you a b dash plus b a dash of root d. Okay, so this is this shows that this is again an element of q root d. Okay, so it's kind of you can say that this, if you define by this way multiplication, then this is closed under the multiplication also, right? So so now question is that if you define this operation by this, does this forms integral domain or not? So clearly this is obviously this is a ring of, I mean, so to show, I mean, you show that this is q root d uh, is a ring actually subring of C, actually subring of that complex numbers. Okay, it's a ring under the above two operation. Okay, so under this above two operation, this forms a ring. But now, can you say something more about this? In fact, we can say that this is not only this is not only a ring. This is actually integral domain also, that else you can prove, and much more actually. This is actually field that we are going to prove it. Now, how do you prove this is a field? So you need to prove that any two non-zero element is a unit, right? So let you choose a non-zero element. So let you have a plus b root d is not equal to 0 in q root d. So what does that mean? That means that is your a not equal to 0 and b not equal to 0. So both are not equal to 0 element. Okay. So if both not equal to 0, then I need to show that this is actually invertible. Okay. But before showing that it is invertible, so you try to um, uh, check that. Now check that your a plus b root d into this a minus b root d, how it look like. So this is of this form, obviously a into a square, and then a plus b minus b square, so this is b square into d, right? Now d, obviously I chose d not equal to 0. Remember, d not equal to 0 is not a square free, so it cannot be 0 also. So this number cannot be 0 because a not equal to 0, b not equal to 0, right? So what does that mean? That means this product equal to something is not equal to 0, and hence this you can talk about the number a minus b root d divided by a square minus db square, right? This is non-zero element. Now see, this is the inverse of this a plus b root d. Okay. Now this inverse is also element of this. Why? Because you can write down that as a by a square minus db square, and then yeah, so then plus of minus b by a square minus db square into root d, right? So this is again an element of q root d, because a b d all are rational. So this is a rational number, so this is element of q root d. Okay, so this proves that this forms a field, and this also integral domain, right? Because every, so this, okay, so one thing you need to first check, the fields are all so another example I should say, every field is an integral domain. Okay, why every field is integral domain? Because example, this is not exercise. Why every field in integral domain? Because here every non-zero element has a inverse, right? So, because so as every non-zero element in a field is a unit, so they cannot be divisible, right? So they cannot be zero divisors. Zero. We can't be zero divisor, right? So what does that mean? That means in a field there is no zero divisor, right? So it must be integral domain. Okay, and the previous example tells you that this is obviously field, so this is also integral domain. Clear? So there are so many examples are there. In fact, we can have some more example in future. But let me now discuss some. Okay, one more remark I would like to tell here in this set. Okay, remark. So, um, or rather, I can say properties, maybe properties. Okay, so the inside the integral domain, the cancellation property holds, right? So we should write down the cancellation um, property holds uh, in an integral domain. What does that mean? That means that that is if suppose A, B, C, you have three elements inside a ring. If three elements inside a ring are then with AB equal to say AC, then either A equal to 0 or B equal to C. Okay, so in particular if A not equal to 0, then B equal to C. Okay, so how do you give a proof? So the proof is simple, just property of integral domain. So it is given that AB equal to AC, and then this implies AB minus AC equal to 0. Now use this distributive property of ring, so A distributed over B minus C is 0, right? Now because as R is an integral domain, either A equal to 0 or B minus C equal to 0, right? By definition, which what we discuss, and that means that B equal to C, right? So in particular, if A not equal to 0, then B equal to C. Okay, so these are small properties. Now, what was the problem I was discussing a little bit earlier? That that we proved that the fields are always integral domain, but converse is not, right? every integral domain may not be a field. For example, ring of integers, they forms the integral domain, but they are not that's not a field, right? Now the very important question: what about the finite integral domain? Um, questions. Do you know? So, what about this finite integral domains? Okay, the answer to this question is that it's a theorem, and this theorem tells you that every finite integral domain is a field. Okay, whatever if you choose a integral domain is finite, then it must be a field, right? We need to give a proper proof of this statement. So proof. So let R be a finite integral domain. Okay. So we need to prove that R is a field, right? So what does that mean? Then I need to choose an arbitrary element. So and say X belongs to R, be any arbitrary element. Okay. So what I need to check? I need to find out that X must be an unit inside R. So what does that mean? That means there exists another element, say X dash or something, such that X into X is equal to identity, right? And then X will be unit inside R. So every non-zero element is unit. Okay. So let me assume that and 0 not equal to X. Arbitrary element inside R. Okay. So every non-zero element is a unit, and then it becomes a field. So this is the assumption is given. Now consider the map. So let me define a map, say phi from R to R by you are sending any element of R to say R times X, for example X. Okay, or X or it doesn't matter, whatever you choose, because R is commutative, right? I choose integral domain, so this must be commutative. Okay, so so this is my map. Okay, so now what can you say about this map? Can you say anything nice? So maybe 1 1 on 2 injective. So the claim is injective. Okay. This is my claim. Now how do we prove this kind of claim? So proof, select phi of say R1 equal to phi of R2 for some R1 R2 belongs to R. Then what happens? Then by definition this is R1 X and R2 X, right? Now you can use the cancellation property, or you can use that like that integral domain. By the product of integral domain, you can say that this equal to 0. Now as X not equal to 0, R1 equal to R2, right? So as R is an integral domain, then you can have this, right? So what does that mean? That means here this map phi is 1-on map. Okay. Now do you know something, that if you have a finite set and then every 1-on maps onto and every onto maps 1-on, they are equivalent actually. So if you have a finite set, then 1-on map, onto map is same, and so that means that every 1-on map is bijective map, every onto map is bijective map, right? Now if you don't know, then let me tell you that how do you prove these things, that on a finite set, on a finite set A, every 1-1 map is onto, and vice versa, and conversely also. Now this is obvious, so let me this one proof that if you have 1-1 map, this is onto map. Okay, how to prove this kind of statement? So if I is, for example, you have a phi map from A to A is 1-1, then what happens? Then 1-1 means what? That means that the range contains, see, for every element it can, I mean there are no two elements can map single element, right? There is a minimum 1-1, right? So what does that mean? So the range at least has the number of elements, right? A range can be bigger than that also. This I don't know, I'm just trying to first see. Okay, so what does that mean? So this phi of A, this cardinality, this is at least the cardinality of A, right? At least, because for every element of phi of A, you know that there is only one pre-image there. So this is the thing, and also, and again, obviously, again, as phi of A is a subset of A, so phi of A actually has at most a many elements, right? So what does that mean? That means phi cardinality of phi of A equal to cardinality of A, which is subset of A. So thus phi of A equal to A. So what does that mean? That means that the range of this phi is full set A, right? So phi is onto, right? So every 1-1 is onto, and this I am going to use it now. I said that this map phi is 1-1, so thus phi from R to R by this phi of R equal to Rx is also onto, right? What does that mean? That means that every element has a inverse P image, right? So again, you see that R is a integral domain, so R contains one, right? Integral ring. So there exists some x dash belongs to R such that phi of x dash will be equal to 1, right? What does that mean? That means what is phi of x dash? It is x dash into x, right? But this is commutative ring, right? So that means both are same. Thus x is a unit and R is a field, right? Every non-zero element is a unit, so R is a field. So this is a proof that finite integral domains are always field, and there is another concept called division ring, which is uh, um, it's not commutative. So what is a division ring? So let me define it. So division ring. Did I define it? I don't remember. Okay, division ring. What is it? So um, remember one thing. So inside field, what was the assumption? The assumption was that you have identity is not equal to 0, but it also that is with respect to multiplication is also abelian group, right? So that abelian is I don't want, right? So so a ring R with unity uh, mm, unity means I am assuming the 1 not 0 is called a division ring. Sometimes it is called also skew field. So let me write down both. Skew field. If every non-zero um, element is a unit. Okay, what does that mean? That means every non-zero element has a multiplicative inverse. But it is, I am not assuming this is commutative ring. Okay. So in addition, this plus commutativity. So if we assume this commutative property, then it becomes a field, right? So what does that mean? The division ring plus commutative property is a field, right? Okay, so um, hmm. Okay, what we are discussing? We're discussing about from finite integral domain. Okay, that is a field, and maybe I will give some example, but maybe I should tell you one more definition. So definition of a subring. Okay, so let me define this. So let you have this R plus dot be a ring, a subgroup R dash plus the subgroup of R plus, okay, is called a subring. So what does that mean? That means you start with a subgroup, it has to be as a subgroup structure of R if what happen if this restriction map. So you have dot from R to R to R, right? Now if you restrict the dot on R dash, it will be a map from R dash cross R dash. But I don't know if it map to R or not. But if this restriction map is a map from R cross to R cross, then if this restriction map is also is that, what does that mean? That means this set is also closed under multiplication, right? That is if A and B belongs to R dash, then okay, first of all, for subgroup, what you know, A minus B belongs to R dash, and for this property, what you need, A into B belongs to R dash. So this is the property you need to check something is a subring. Okay. And in particular, if the subring contains identity, then you don't need this minus property, because minus becomes negative of 1, right? In that case, if 1 belongs to the subring R dash, then what you need to check? You need to check that for all A B belongs to R dash, A plus B belongs to R dash, and A into B belongs to R dash. Why? As A minus B can write down always by A plus minus 1 into B, right? And minus A B belongs to R dash, minus 1 belongs to R dash. So by this property it is an element of R dash, and then if we add it, then by this property it is element of R dash, right? So this is obvious now. Okay. Now can I get some example? Yes. So there are examples. So examples. So you start with that real numbers R plus dot. Usually sitting inside C complex number, right? But again, inside real number you have this rationals Q plus dot, and this is also inside this you have integers Z plus dot. Okay, these are all subrings. Okay. Similarly, the non-subrings, so you start with Z plus dot, and you have say 2Z plus dot. This is a subring. Okay. Now there is a catch. Some people use the fact that if the identity is inside the ring, then the subring must contain the identity. Some people use that fact, but generally I don't use that fact. Okay, so I said that it's kind of is closed under both the additive, and so it's kind of subgroup with respect to addition and this closed under multiplication. So kind of these structures. Okay. Okay, so this property tells you that you can always find out lots of subrings, and in fact, remember we defined these quaternions, so you can have some more property. For example, these Hamiltonian quaternions. Remember A plus Bi plus Cj plus dk, and this with the property. These are real numbers, and then you remember I square equals j square equals k square minus 1, right? So here you can have a subring, say h dash, so of this form, a dash, b dash, c dash, d dash. Okay, I'm just taking this ai, a dash, b dash, c dash, d dash are elements of the integers. Okay, so they are also they are actually the forms of subring. Okay, this is simple proof. You can check that this is h dash is a subring of subring. I mean, obviously subgroup, there has to be first subgroup with respect to addition, and then close under multiplication subring of h. Homework. So this is a simple property. Okay, maybe I will stop here, and you can do lots of other examples. Okay, and in next tutorial there will be lots of such problems. You can solve those things. Okay, so I will stop here today.